Hi there, welcome to this video. We are going to talk about rates of change of polynomial functions, and this is lesson 3 in unit 1A. We're learning to use rates of change to identify a function specifically from a table of values, which is a common question in the AP Precalculus exam. You'll see this type of question on multiple choice as well as possibly on an FRQ question. So what we're going to go ahead and do is calculate rate of change from a table of values, hopefully which you are familiar with. We'll be able to interpret the rate of change from a table of values, and then we'll construct a written justification using rates of change. So let's go ahead and dive in. Rates of change can be used to determine what type of function model is best for a table of values if the input values are in consecutive equal length intervals. So input values are consecutive equal length intervals. Now what I like to do here is I like to call this ELIVy. ELIVy. And this is just an acronym to help you remember. You cannot use this as an acronym on the exam as it's not widely accepted. But what this says is equal length input value intervals. Equal length input value intervals, okay? And so you can go ahead and see an example of this here. My input values are adding by 1, 2 to 3, 3 to 4, 4 to 5, okay? Now, for a linear function, y equals mx plus b or ax plus b, rates of change will be constant, right? And this makes sense because if I have a linear function, which we're seeing here, then I have a constant slope, right? So my rate of change is constant. And we say the first rates of difference are constant, or if I took the rate of change of the rate of change, right, it would be 0, right? So my rate of change here to here, let's say, is 1, and then my rate of change here to here is 1. Well, the difference between them is 0. So second differences would be 0. Now, what about a quadratic function? Oh, and actually, so I want to go ahead and show you in this table here, right? So from -1 to 1, that value is 2. From 1 to 3, that value is 2. From 3 to 5, that value is 2. So notice how your rate of change is constant, and then the rate of change of your rate of change is 0. Okay, so first difference is constant, second differences are 0. That's for linear. A quadratic function. Notice again how I have equal length input value intervals here. 4 to 5, 5 to 6, 6 to 7. I'm adding by a constant amount. And my output values are not changing at a constant rate. So here I increase by 12, then I increase by 20, then I increase here by 28. Okay, so this is definitely not linear, but if I take the second differences, that has a difference of 8. This has a difference of 8. So the rate of change of the rate of change is constant. Our second differences are constant. You could also say that the rate of change is linear. So I have a linear rate of change. But again, I kind of like this explanation here for quadratics. The change in the rate of change will be constant. Okay? And so sometimes, again, the change of the rates of change is also known as the second difference. Now, these questions, or these types of functions, don't really appear on the AP exam, a cubic function and a quartic function, but it is relative in the sense that the same kind of pattern goes on. So for linear, my first difference was constant. For quadratic, my second difference was constant. For cubic, what do you think the difference will be? So here, I increase by what, 1? By 1, by 7, and then by 19. Okay, so that's my first difference. Second difference, 0, 6, and then here we get 12. Okay, so now maybe you see a linear pattern, and then let's look at the third difference. The third difference, 6, 6. My third difference is constant. So for a cubic function, your third difference is constant. For a quartic function, what do you think is going to happen? Yes. The fourth differences will be constant. So if I went ahead and did that, that's the pattern that you would see. I'm not going to spend a lot of time and focus on this because it's not really relative to our course. Okay? Let's go ahead. Let's look at an example. This is a type of question that you'll see on the AP Precalculus exam. Let f be a function defined for x greater than 0. The table gives values of f of x for selected values of x. And what you notice right away is that we have consecutive equal length input value intervals, right? I am adding by 1 for my inputs, and then my outputs, notice that I am subtracting 11. I am subtracting 13. I am subtracting 15. So these values aren't constant, so this is definitely not a linear function. But if I analyze the change of the rates of change, it looks like here I'm decreasing by 2. And that is constant. So this is a quadratic function, And this is set up for an FRQ question, which will be the free response section of the exam. And question A says, use the table values of f of x to determine if f is best modeled by a linear or a quadratic function. So all we do here is we just analyze, or we just write the function, quadratic function. And then part B says, give a reason for your answer based upon the relationship between the change in the output values of f and the change in the input values of f. So we are going to go ahead and say it's quadratic function because the change in the average rate of change is constant, adding by 6, over equal length input value intervals, where we're adding by 1. Okay, so the change in the rate of change is constant. Not adding by 6, we're actually subtracting by 2. That's our constant change of rate of change. Subtracting 2. Okay, so I reference the values in the table. Okay, so the change in the average rate of change is constant, which we're subtracting by 2. Okay, over equal length input value intervals, which are just adding by 1. Here's example number 2. Let g be a function defined for x is greater than 0. The table gives values of g of x for selected values of x. So let's go ahead and analyze this one. Notice, what you should notice about this, they are kind of trying to trick you here. Your x and your input and your output values are flipped. So your x values increasing by 1. Output values, I'm adding by 4, adding by 4, adding by 4. Hey, my rate of change is constant. So that means that this is a linear function. Give a reason. Well, we can say the average rate of change is constant, adding by 4, over consecutive equal length input value intervals. Which are adding by 1. Okay, so again, what is the average rate of change doing over your E-Livy? So rate of change over E-Livy is how you kind of generally remember this sentence frame. The average rate of change is constant, adding by 4, over consecutive equal length input value intervals, which are adding by 1. Okay, here is a practice problem. Please go ahead, pause me. I want you guys to answer both of these questions. So what type of function, linear or quadratic, and then give a reason. Okay, here we go. This is a linear function. Your average rate, your output values are subtracting by 20, so your average rate of change is constant, over consecutive equal length input value intervals, where you are adding by 1. Adding by 1. Okay? All right, did you get it? Hopefully you did. Here is multiple choice questions. So these questions can again also appear in multiple choice sections. So here's an example of this one. Go ahead, pause, and then we'll look at the answer here. Okay, looking at this one, this is going to be a cubic function. So it's not quadratic, A, and it is not C. It's between B and D. And let's look at the reason why. They say because over consecutive equal length input value intervals, the second differences are constant. No, we want our third differences to be constant, right? First differences, second differences, third differences are constant. Another appropriate answer would be to say the second differences are linear, where we have, that linear relationship. Okay, go ahead, same type of question. Pause me here, answer this one. Okay, here is the rate of change. Looking at this is going to be a quadratic. It is definitely not linear because our first differences are not constant. The first differences are actually linear. They have a constant rate of change of 2. The second differences are 2. So let's look at these. B, G is best modeled by a quadratic function because over consecutive equal length input value intervals, the change of the rates of change is 0. No, that's the definition for a linear. So let's look at this one. Best modeled by a quadratic because over consecutive e-Livy intervals, the change of rates of change is constant. This is true. That is true. Okay, so D. All right, next part. We're going to go ahead and talk about concavity again. Recall that where a function is concave up, the rate of change is increasing, and where a function is concave down, the rate of change is decreasing. Also recall that when a function is increasing, the rate of change will be positive, and where the function is decreasing, rate of change is negative. Okay, so how's this going to tie into what we are doing? We are told that the table of values, or the table gives values for a polynomial function p at selected values at x. Which of the following could be true about the graph of p of x on the interval 5 to 8? And notice our options are saying the graph is p is concave up and it's concave down because about the average rates of change. So let's analyze the average rate of change. Notice that my outputs are increasing. So my average rate of change is positive. I know that this is going to be an increasing function. But how are the average rates of change changing? So I'm increasing by 9, then I'm increasing by 6, then I increase by 4. And it's important to note that this is over consecutive equal length input value intervals, right? So you can analyze that slope. So notice I have positive slope, but my positive slope values are decreasing. I'm increasing by less and less each time. So if my rates of change are decreasing, that's going to be concave down. So I'm going to get rid of A and C. This is concave down. Let's check the answers here. Because the average rates of change over consecutive equal length input value intervals is increasing. That's false. That would be concave up. So D, because the average rate of change over intervals is decreasing. All right. Go ahead, please pause me and try this example. All right, hopefully you got D. The graph of P is decreasing and concave down. You can see that this graph is going down, and the rates of change are getting more and more negative. Okay, so that is decreasing. -4, then -6, then -11. Decreasing. Okay, so concave down. All right, last question here. It says the table of values, or gives the values of f for certain values of x. The function, if the function is linear, what is the value of f of 17? Okay, so what we want to do is, if this is a linear function, what this means is that our rate of change is constant. And so you can go ahead and you can look at this. So here my output is going to be changing by 2 over my input, which is changing by 8. So that means that my slope, m, is equal to 2 over 8, which is 1/4 per x value. So if I want my f of 17 value, I got to go ahead and I got to start somewhere. So I guess I'll start here at the x value 10. So I'll start with f of 10, which is equal to 5. and I'm going to add my average rate of change for each value that I am increasing by. So since I'm starting at 10, I have to get to 17. So that is 17 minus 10. I have to apply this average rate of change for 7 values. So this gives me 5 plus 7 fourths, okay, which I can make this a fourth, 7 fourths, which gives us 27 over 4, which is almost 7. I guess we get, 6 and 3/4. I like 27 over 4. There you go. Okay, so hopefully in this video you learned about average rate of change and how that relates to identifying functions. Linear function has a constant average rate of change. Quadratic function, the change of the average rate of change will be constant. Okay, go ahead and like the video if you learned something. I'll see you in the next video.